Hello fellow data experts. At Varigence, we work hard to keep up with the latest in technology so that our customers, you, can apply these to your data solutions either by reusing your existing designs or rather your design metadata and deploy this in new and different ways. Or of course when you start new projects. Some of these technologies can make you wonder what a database is these days. A good way to think about it, at least in the context of a relational database, is to consider what a database actually does for you under the hood. A good example of this is transaction isolation following the ACID principles. Transaction isolation is the mechanism by which the database makes sure that transactions that modify the data are separated and through this manages the way concurrency is handled. For example, it can prevent the data that is used by one transaction is used by another one until the first transaction has been successfully completed. This is part of the ACID guidelines that underpin the inner workings of a relational database management system and how it keeps our data safe. ACID stands for atomicity, consistency, isolation, and durability. Atomicity means that each operation is managed as a single block. So either it works or it doesn't. And this involves commits and rollbacks and things like that. Consistency looks after the integrity of the data following rules that have been configured or are configurable. For example, using constraints, references, but also being able to rebuild or replay transactions from a transaction log and then, of course, get the same outcome. Isolation makes sure that individual transactions from potentially multiple parties do not interfere with each other. For example, managing reading and writing data at the same time. So this is where dirty reads can come from, depending on your configuration and implementation of row versioning and locking and stuff like that. And last but not least, durability means that the successfully completed transactions, the data, will remain even if things go wrong, such as when the system itself fails. When your database goes down and then gets back up, hopefully, you would expect the data to be still there. But what happens when we don't use a relational database? At least not for some of our layers or areas in our architecture. For example, when we use a data lake for our persistent staging area or even for a data vault. Well, these days there's even more options to consider, and one of them is the topic of today's presentation. I'm Roland Vos. I'm a data specialist and I sometimes refer to myself as an automation enthusiast because it's fun. What can I say? Over the years, I've been working in the data area as a consultant, as a trainer, as a software developer, and as a manager in the corporate world. Data solution automation, so the ability to forward engineer your data solutions based on your design metadata, has been a consistent element throughout these years. So it makes sense that these days I'm working at Varigence, which is the leading software vendor for data solution automation. You may have heard of BimL, the BI markup language, especially if you've been active in the Microsoft space. Varigence has been providing that for 15 years now, almost, so it's quite a big deal. The BimL domain-specific language has been around for as long, and it's helped lots of companies and individuals to make generating components for the Microsoft stack much easier. We developed a product called BimlFlex, which allows you to design and manage your data solution and then forward engineer the structures and the data logistics processes, the ETL if you will, for a variety of architectures. By using BimL, the data logistics output that is generated will be native for whatever the target platform is. So if you configure Azure Data Factory output, you will get fully fledged pipelines and mapping data flows. And once you've deployed these to Azure Data Factory, you can run these independently for BimlFlex if required. BimlFlex really is meant to design and deploy your solution. The operation of the solution can be done in the platforms that are designed to do so, such as Azure Data Factory. Today's webinar is about one of these terms you may have heard recently, which is the lakehouse architecture. It's one of those terms that sometimes makes one wonder why you need it, but for today, it may help to explain how you can mix and match different technologies to make sure your data solution meets the requirements of certain use cases you might have. In principle, This approach offers opportunities to work with various kinds of data in a single technical environment. For example, combining semi or unstructured data or batch and stream processing. It means that various use cases can potentially be supported by a single infrastructure. We'd like to cover how using a framework for automating your data solution, such as BimlFlex, can assist in adopting these various technologies. From our point of view, though, it's all about managing the design metadata and being able to deploy this in different ways so that we can meet specific and unique requirements. The Data Lake is an example of this. So Microsoft has made Data Lake connectors available for Azure Data Factory pipelines and mapping data flows. Using these connectors, you can use your data lake to act as a relational database for delivering certain target models, while at the same time use the data lake for other use cases. Data Lake is an open storage layer that can be used on top of Azure Data Lake Gen 2, where it provides basic transaction control features, the asset guidelines that I mentioned in the introduction, to what is otherwise a file-based data lake. Even better, mapping data flows can use Azure Data Factory integration runtimes for the compute without requiring a separate cluster that hosts the data lake layer. This is the inline feature, and it makes it possible to configure an Azure storage account, the Data Lake Gen 2, and use the Data Lake features without any further configuration. The compute or the processing happens on the fly, and the data lake is used for storage. So you can connect your data lake this way as if it were a database. This means that it's perfectly possible to build your entire data vault solution without actually using a traditional database, a Delta Vault. When all you need is a data lake, your technology footprint is relatively light. It's easy to set up, it's easy to manage, and it is relatively cheap. And this setup can be done really quickly by simply creating a new Azure storage resource, which can be done with a few clicks in Azure or by running a script. At the same time, though, you're still building a data solution using the same data concepts as always. In this sense, a lakehouse is just another way of doing things you're familiar with. But there are some new tricks you can add to the mix, especially related to Azure Data Factory automation when it comes to adding more complex transformations, which you will need in order to deliver a data vault. You can essentially apply complex logic against the files in the data lake and perform transformations on your data this way. You don't need to load it into a database first. As with all technologies, including terms such as Data Lake, Data Vault, or Lakehouse for that matter, this will not absolve anyone from the need to do adequate architecture and data modeling in order to get the correct data outcomes. Data management and data modeling, as we all know, it's a complex domain of which the technology aspect is only one. What we're trying to do, though, is to make this technology aspect easier so you can focus more on business modeling and data modeling. Also, the fact that we can run an entire data vault directly on a data lake does not mean that we have to. It just means that we can prove we can switch out some of the layers in the design with different technologies, and that the overall solution still works as expected if we choose to do so. So let's develop this data vault without a database. Before we start looking into it in more detail, we need to understand a little bit better what a Delta Vault is and how it can be supported by ADF. As I mentioned in the introduction, Delta Lake is an open source storage layer that can be used on top of a data lake. As a separate technology, it can be applied to various types of infrastructure, of which the data lake is only one. A common scenario, for example, is run your own Databricks cluster and configuring Delta Lake storage there. The way you set this up determines the options you have to interact with the data via Azure Data Factory. There are different ways to do this, and using pipelines or data flows offer different features. Fundamentally, it comes down to determining where the data resides, the storage, and where the processing takes place, the compute. For example, you can use an existing Databricks cluster to store files either in the Databricks local storage or by mounting a file or directory in the data lake or some other storage provider. But Databricks will be the place where you would access the data from usually. And when connecting to this Databricks cluster via ADF, you would use a link service, and that would allow you to connect to Databricks in pipeline activities, for example, by using a copy data activity. This means you can run queries against this cluster and access the tables, and which with their files, but they look like tables because of the Data Lake. The cluster will do the compute if you run a query against it, and ADF will catch the results, and you can write this into a sink, a target, as defined in ADF. And Data Lake will manage transaction control. In this setup, you can also use mapping data flows, and again, this can be done in different ways. First off, you can use the same link service you would use in ADF pipelines to connect to the data and push the compute to the underlying layer. The difference is that using mapping data flows, you've got the transformation activities and the expression language from data flows at your disposal to do your data wrangling, right? Your transformations. In other words, you can apply some of the transformations midstream, and you can push down some of the SQL to the underlying cluster and mix and match to get the best outcome. But generally speaking, most of the compute would happen on the underlying cluster, and the integration runtime would be a bit more lightweight. Data flows provides an additional approach which applies to the Data Lake as well. Data flows can use integration runtimes that do the compute without requiring a separate cluster that hosts the actual data lake storage layer. This is the inline feature I mentioned earlier, and it can be configured for the connection inside the data flow. So you connect to a data lake and say this is going to be inline processing. What happens then is that Azure Data Factory will spin up a transient Spark cluster to do the compute. When the processing of the data is done, depending on the configuration you've made, this impromptu cluster will power down again, and all you will have is the Data Factory and the Data Lake again. So you don't need your own external cluster to do the compute anymore. And it's also really useful when the schema, the structure of the data, is not set in stone as much, or to use the term where the schema can drift. It's all very dynamic. This capability to not require an external compute facility provides an additional approach using the Data Lake. If data flows can use ADF integration runtimes for the compute without requiring a separate cluster that hosts the actual Data Lake storage, you can access the Data Lake directly. And this is what can be done using data flows in combination with the Data Lake connector. And this is the pattern we will use today to show how this approach can be implemented. In this setup, we don't need to specify a schema necessarily. We are still able to use the various midstream transformations, and we do not have any infrastructure requirement beyond the data lake. To summarize, ADF pipelines can connect to existing clusters using a link service. This way, queries can be run against the data lake, the Data Lake, but only when a cluster is available. Mapping data flows can also connect to data lakes directly and interact with these as if they were databases using the inline processing as specified for the Data Lake connector. Let's see how we can create a data flow this way. And this is also where BimlFlex comes in. Let me give you a really quick BimlFlex overview so you can see how things come together for automating this pattern. In short, we will use the BimlFlex application to configure our solution. We will import the schema from our data sources, then take a proverbial step back and consider the business context, create a business model that we can map to the incoming data in order to deliver either a data vault, a dimensional model, or both, or something else. You don't necessarily need to do all of this, but this is a bit of a standard workflow. Once the information is available, this goes into our development environment where we can put additional logic and overrides and extensions. We will compile that and deliver the data integration artifacts in native format. These data logistic artifacts like pipelines and mapping data flows, SS packages, SQL scripts, whatnot, that can go into a DevOps workflow. where it can be deployed to a modern data integration platform, where it will be hosted and run and managed to deliver your modern data solution. For this demo, we will use a CI/CD pipeline that performs these steps based on the design metadata of the solution. So I'm going to start up BimlFlex at this stage and show you what the solution looks like. I'm not going to go into too much detail. I appreciate some of you are new to BimlFlex, and I don't want to bore you too much with the details. You can always reach out to us for information or a more detailed session. So let's open up the BimlFlex app and check our design. What we see here is the BimlFlex dashboard, and it provides an overview of the solution. And if you're used to BimlFlex as a tool to work with, nothing really is out of the ordinary here. The key message is that in our flow of data through the layers, we have defined that these data logistics should be done using mapping data flows. And the rest is derived from the connections we're using. And this is what you configure at the project level in BimlFlex. And the project specifies that data goes from a source to a staging area, then to a persistent staging area, onto a data vault. And that this is done using Azure Mapping Data Flows as a template to generate the data integration artifacts with. The connections here are all Data Lake targets, and the data sources are basically a collection of flat files and some tables in the Azure SQL database. The staging connection is a Data Lake system type, which tells the generation engine to deploy code that is compatible with this design. So we've got a couple of sources, flat files, we've got a couple of targets, steps, which are all Data Lake formats, and they should all be generated as mapping data flows and the supporting pipelines to execute them. The only other thing I wanted to bring to your attention is that we have defined two columns as being derived. Our derived column feature is one of the ways you can add bespoke logic to your design so that this is generated into code that is native to the data integration infrastructure you are targeting, mapping data flows in this case. For example, we have the full address column, which is set to derived with the derived checkbox, and we use the data flow expression to add the logic we want to be generated as native code in this mapping data flows target environment. Moreover, we also have a full address upper derived column, which uses the output from the full address and uses that as input for the full address upper transformation logic. The next step is to map these data sources to a target model, and this can be done using a data vault accelerator. We use the accelerator to map the data sources to the data vault model and also link this to the business model. Ultimately, we use the business modeling feature to define a more holistic data vault and then make sure that the various data sources can be mapped to it. This is all covered in more detail in the previous webinars, and I would recommend to have a look at those if you have the time. For now, we've already prepared a model for this demonstration with the data sources that we've just went through. The data vault model is mapped to the data vault Data Lake connection, so the resulting data structures would expect to be delivered in that particular data lake container. For good measure, the containers can be found here in our storage account, and we have one container for each connection we've defined in BimlFlex. So you've got the staging connection here, which is the staging container on the data lake. We also have the data vault, the persistent staging, and we also have a couple of sources defined. So the source flat files map to the directories that you can see here on the screen. We've also prepared an empty data factory that we would use to deploy the generated data logistics artifacts in, so the pipelines and the mapping data flows. And these will all be visible here once we've completed our build pipeline. For now it's empty, but after deployment we would expect that our resources would be created in this location, so we can run them. The whole build process can be automated using DevOps pipelines, and I'll run this one now. This will basically follow the entire process we've covered earlier in the presentation, and it installs the Biml Studio development environment. It will compile the data logistics artifacts, the mapping data flow, etc., and it will ultimately deploy the generated output to the data factory we've just seen, so we can run the processes. This way we can automate the full development process from designing the data vault and the solution in BimlFlex all the way to Data Factory resources we have made available for this. The pipeline has now created the Azure Data Factory pipelines and mapping data flows. So we should be able to go to our Data Factory and look at the results. The first thing to do is to refresh the Data Factory we looked at earlier to see if anything has changed or has been added, which is coming in now. So you can see that there's a couple of pipelines being created, and there's a couple of data flows created as well. Let's open up the address mapping data flow, which contains the derived column transformations we configured earlier. And this is what the result would look like. So the source is in this case, the address comma separated file, which is in our data lake. I'll quickly turn on the debugger as well so we can look at some of the results for each step. So we have the source CSV file here, and the targets that we're looking for are the Delta Lake targets. So this pattern loads the staging and the persistent staging area in one go. There's also a lookup that we've added, and this is all generated through the BimlFlex engine. So here we can find the derived column transformation, and you can see here in the expression that the logic we've provided in the BimlFlex app finds its way into the ETL. And the second transformation will use the output of the first one as input. And because the debugger is now enabled, we can look at the results as well. What you can see here is the interim result that the mapping data flow would generate at this step in the process, at this transformation. And it has the data from the source, and it also contains a couple of framework columns or attributes that are generated based on the definitions within the BimlFlex framework. But equally important, you can see the full address and full address upper columns here that have been added to the data set because of the derived column transformations we've added. To run this as a regular process, we need to go to the pipeline, select the pipeline that calls this mapping data flow, and run this. So the pipeline will do the orchestration and do the integration with the control framework. For example, logging how many rows are processed, where loaded, where inserted, how long the process takes, and also if everything went successfully or if there were any failures and any sort of maintenance needs to be done, stuff like that. So the wrapper around the execution of the mapping data flow. So let's kick off the process, have a look. And in the meantime, we can start opening up our storage account, our data lake resource, to see if anything's happening in the staging container. And it is. So the process would have created the directories and files it would need to. And the address file was the file we've been processing for this particular ETL process. But if we look into the directory, there's a whole bunch of little files that make less sense. And this is how Delta Lake works, because every individual file that you have in these directories that is created is a part of the table, is a part of the data set. So these are all mini partitions in Parquet format. And if we open one up, we can see what the contents are, because we can view Parquet files. And it looks like this. So this is, in this case, one record, which is a very small subset of the table. But we can still see that the derived information is available. Every directory in the Delta Lake would have a Delta log directory as well. And this is the internal way that the Delta Lake manages the transaction control from the introduction. So all these Parquet files and all the changes in the data set as a collective, they're tracked in the transaction log in the Delta log table. And the same would apply for the ODS or the persistent staging area as well. So if we go to the ODS or PSA container, we would have the similar directory structure as we would expect from the staging area, including all the Parquet files and the Delta log table. So with this information, we can start loading the data vault. It's a similar setup. There's execution pipelines that ultimately call the mapping data flows. So let's start looking at the data flow first. The pattern for this mapping data flow for data vault, it basically loads the data from either the staging area or the PSA and populates it into whatever target structures are associated with it. So it will pick up the single data set and load it into one or more target tables. In this case, it's a hub and a satellite. So the targets are Delta Lake I should say, Delta Lake targets, and the source is the Delta Lake staging source in this case. So now we can start running it, and we can look at some of the results in our data vault. So let's see what the ADF does and tracks the process for. And it's running. So now the process is running, we can start looking at our storage account again, the data vault container. And in this case, an RDV directory is created with two tables or directories. So the hub address and the set address. And again, it has the Parquet files. But if we open one of these, it will have a more familiar satellite structure that we can review. And here we go. And the satellite has the natural business key, which is one of the patterns that I really like, as well as the regular data vault. So those load date timestamp and things like that. And of course, the derived columns that we have. And have a look at the full row hash. I've generated this specifically to be readable. So I didn't actually hash it, but I loaded the values pre-hashing, if you like. And the reason is that now we can look at the way this is all done. And one of the really nice things about working with mapping data flows is that everything can be fully dynamic. There's no schema set, right? We use the inline option. So the schema is derived on the fly effectively. And the information on how to define hash, full row hashes and things like that, that can be made fully dynamic based on the information that's passed into the mapping data flow. For example, if we look at the formula here of the full row hash, it uses the built-in dynamic logic that mapping data flow has to basically take an array of values and turn it into a hash. And this, of course, is generated through BimlFlex as well, but it allows for a lot of flexibility to inject metadata into the mapping data flow based on whatever we feed it with the pipeline. If we switch back to the pipelines, there's a really cool feature that BimlFlex has, and I'm going to start this now so we can get the process running while we talk. But there is an opportunity in the development environment to add extension points to basically add any kind of other logic that you may want in the framework. So these are patterns that are not specifically generated from the BimlFlex generation engine, but these are things that you can add to the solution, and they are saved and managed as part of the solution. So this particular pipeline, it basically picks up one specific directory, i.e. table in the Delta Lake, which is the set address, as a source, and it saves it back to a SQL Server sink or a target. And what I want to do with this is just to show that these Delta Lake directories, they basically act as any other table for the purpose of loading data to a different location. So the process is still running. But if I go to my management studio to look at the target server that I've loaded the data into, there should be an export table there that contains the result basically as a dump of the set address that lives in the Delta Lake. And that's pretty cool. So this is just something that you can add to your solution, also just to show how the Delta Lake can interface with any other platforms as easily as anything else. So last but not least, one of the really fun things I always like to do is to develop solutions for complete rebuildability, and this includes the data vault as well. And the good thing is we can just delete these directories from our Delta Lake and rebuild them again using the same processes based on the data that's captured in our persistent staging area or equivalent solution that captures the historical transactions that were ever received by the data solution. So this is how you can use BimlFlex right now to test out these technologies for your design. The mapping data flow feature is still in preview because we're still working to achieve full parity with the other features, similar solutions that BimlFlex provides, such as generating ETL for SSIS, various types of SQL scripts, and of course the pipelines in ADF with copy data activities and the orchestration. So we want to make sure that that's all done before we say it's all good to go. But it's already functioning, at least for the use cases that we presented today, so please check it out. And also keep an eye out on the Varigence blog, or for the Varigence blog, where we regularly post development updates, including progress on supporting Delta Lake. As always, it is a pleasure to share information on these topics. My contact details are on the slide deck, so please reach out if you want to know more. To summarize, we've looked at what a Data Lake is and how ADF supports it. We have then used BimlFlex to generate the data logistics as mapping data flows that implement a data vault design using only a data lake resource in Azure. And we can query and interact with this as if it were a database. This gives us another technology in our tool belt to architect our solutions with. We can then decide how we want to implement certain layers or areas of our architecture in different ways. Using Data Lake, we can use the data lake for both database-like operations as well as streaming and file-based operations. If you want to know more, please reach out to us at any time for a more in-depth conversation, a proof of concept, or a demonstration. Thanks for watching and hope to talk to you soon in person.